Hello, I'm Trent. I'll be explaining part 1 of lab 3. So as you can see, this is the part 1, this is the circuit, and this is the state table. So as you can see here, I have drawn the state diagram. It will go from 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1, and back to 0, 0, 0 again. As you can see from this 0, 0, 0. So it will be true for this. So I will be answering the question, how can the state of flip-flops be forced to a particular value to allow the transient states to be checked? So the only input we can change is about the Ka and Kb, where it's 1 right now. So if we force the Ka and Kb equals to 0, so the state will only be set or hold. So A and B will always be 1, and the C will interchange from 0 to 1. So by releasing the K right here, this will change to it from 0, 0, 0 to back to 0, 1, 0, and then interchange between this value. So when I switch off the K, it will be like this. It will rotate. It will interchange from 1, 1, 1 to 0, 1, 1. So to change this, I'll just wait until I get the wanted value and then press the K again. For example, this is for the 1, 1, 1. See, it goes back to 0 and then continues on. So I release now to check for this. This 0, 1, 1 will go to 1, 0, 0. 1, 0, 0 and back to and follows the state diagram. That's all. Thank you. Hello, I'm Trent. I will be explaining part 2, and the circuit I've built is the second one. Implement the function, this function using an 8-to-1 multiplexer and a single gate. Here's the truth table for that function. And this is the theory of the 8-to-1 multiplexer, and this is the truth table when expand. So from this we can see that B, C, D are the S1, S2, S0, and then the A is actually the input. So in order to use one single gate, so that we can use one inverter gate right here. This is the schematic. As we can see, only one inverter gate used right here, and others is just straight input from A or ground or 1. This is the circuit. Look, these 4 bits will be indicating like the number A, B, C, D, and the last bit outside will be the result. 0, 1, 2, 3 light up, 4, 5, 6, 7 doesn't light up, 8, 9, 10, 11, 12, 13, 14, 15, back to 0. That's all. Thank you. Hello, I'm Tran. I'll be explaining part 2, the continual part, where we will construct a circuit that implementing this function table using actually a 3 to 8 decoder and one single gate. So this is the truth table that we have, and then according to this table we must get this output. So therefore we've picked the Q2, Q2 and Q4 and Q5 to this, and what we can get the exact value from here is using the triple NAND gate, as you can see from here. And this is the schematic for the circuit. This 3-bit will be the LED that indicating the ABC, and this outer LED will be the result. So 0, 1, 2, 3, 4, 5, 6, 7. That's all. Thank you.
I'm going to explain about part 3. The first part. From the script we get this boolean, and then from this boolean we demorgan it, and then we can get this equation. From this equation we can know that the K-map will be this. So from here we know that the hazard happening here, and because this is SOP, so we know that this is static 1 hazard. We force A and C to 1, and then for B we connect it to clock so that we can change it from 1 to 0, then we can know the hazard. So from the graph, here is 1 and then here is 0. When the B change from 1 to 0, the hazards will change from 1 to 0 and then back to 1 again. And that's how I'm going to present part 3, the second part. To fix the hazard, we need to add this group. So from here, which is SC, after this we De Morgan it, and then we will get something like this. Then this is the circuits, and from this circuit we can know that there is no more hazard, because from the graph here the hazards O is 0.